like this. Okay, very good. Out of the way. Is that okay?
Yeah. So we should go more or less until 10:45, and then we have a coffee break.
Yeah, got it. Got it. And we'll have a coffee break then. All right. So, so today we're going to revisit the same theory we were talking about yesterday, this colored trace phi cube theory. And we're going to talk about the same kinds of ideas, but from a different point of view. I won't really explain in detail the sense in which this point of view is kind of dual to the point of view we were talking about yesterday, but I'll sort of indicate as we go along the sense in which that's the case. In this morning lecture, I'll again begin essentially talking about things at tree level, but we're going to now talk about things from a point of view where every concept is going to make sense to all loop orders. Okay, so all right, so let's go back and start a little bit more systematically with the simplest theory of colored scalars. So again, we have some scalars phi ij run from 1 to some capital N, and so this has a UN global symmetry. In this case, it's not gauged. And our Lagrangian was trace of d phi squared plus some cubic interaction third g trace of phi cubed. And as we talked about, a phi propagator has two indices, right? So this is the upstairs, let's say, and the downstairs index. So the I and the J. And so the interactions look like this. Now, just very specifically, what do I mean when I say the interactions look like this? What I mean is that, what is this trace phi cubed interaction? It looks like phi ij, phi jk, phi ki, right? So we can really write this as a phi I1 J1, phi I2 J2, phi I3 J3, with a bunch of delta functions, with a bunch of delta deltas, right? So this has got some delta J2 I1, delta J3 I2, delta J1 I3, for example. Okay? So what these pictures are just a way of encoding what the deltas are. Okay, so when I write something, when I write this down, really I have 6 indices here, right? So here I have some I1, J1, I2, J2, I3, J3. Okay, and so this picture, the lines in the picture are just deltas. Okay, so when I write this down, it's telling me there's something going upstairs here, downstairs on this side. So delta I1, maybe I should have written this, sorry. It's delta I1, J2, I3, and so on. Okay, so these lines are exactly telling me about the pattern of delta contractions that I have. So we don't draw them explicitly. We don't draw the indices explicitly anymore. But the actual amplitude is some big tensor that's made out of deltas, right? And so we're just breaking up that tensor into the sum of different pieces with different patterns of how the deltas are contracted with each other. And each one of those is one of the color orderings. So maybe when Yara talked about color ordering, Sometimes it's talked about in the language of traces, like trace TA1, TA2, et cetera. I'm just talking about it in a slightly different language, directly in terms of the indices that the amplitude has, right? It has upstairs and downstairs indices, and so different patterns of how those upstairs and downstairs indices are contracted are associated with different color orderings, right? So if I have the ordering 1, 2, 3, 4, it means that the deltas are contracted between the 1 and the 2, delta I1, J2, delta, right? So between 1 and 2, 2 and 3, 3 and 4, 4 and 1. If I say it's 1, 3, 2, 4, it's just the deltas are contracted in the similar way with those particle labels on the outside. Okay, so just okay, so from now on, we won't write the indices anymore explicitly for that reason. Okay, but this is the basic pattern of that's our basic 3-point vertex. And so then we can talk for any given ordering about these color-ordered amplitudes, and they're all associated with these fat graphs, like we said yesterday. Okay, so at tree level, I would have this fat graph and this fat graph. Let's say at 4 points. And I might stop drawing the arrows as well, because the arrows are just fixed. They're just upstairs and downstairs arrows. At one loop, I could have something that looks, for example, I could have a diagram that looks like this for 4 points. Or I could have a diagram that looks like this. Okay? Is this all clear? All right. And of course, these pictures are famously associated with Tufts topological expansion, 1/n expansion for any observable, of course, including amplitudes here. And so we see some of the famous standard things. For example, here at tree level, if this thing goes like G, this amplitude will go like G squared. There's 2 Gs. This amplitude goes like what? This goes like, well, there's a G here. There are 4 Gs. It goes like G to the 4th. Okay, but notice that there is this, if I put the arrows back, there is this arrow here, which is not associated with, is not determined by the external colors, right? So we have to sum over all the colors that go in there. So there's an extra factor of n that shows up associated with that guy. Okay, so similarly, there's a G to the 4th n associated with this guy. Let's look at, let's keep on going by drawing these colored pictures. I'm just reviewing standard facts about the topological expansion, but if you haven't seen it before, it's also extremely, extremely simple. Let's draw some more diagrams at one loop. These are things that you can call single trace pieces of the amplitude. Single trace because in the end, if I draw the arrows, there's just one pattern of arrows going around, right? This contracts with that, this contracts with that contracts with that, right? So there's just one pattern going around. At one loop, we could draw something else. We could draw double trace things. So for instance, I can have something that looks like say, just to pick an example, all right? Okay, is it clear to you why this is called double trace? Because what is the pattern of deltas here? The guys on the outside, 1 and 2, contract with each other, right? This goes with that, this goes all the way around and comes back, right? So that's one trace factor. There's another trace factor just with this guy on the inside, okay? Or, you know, I could put another one here if I wanted. Okay, so this would be a 4-particle amplitude, okay? Double trace 4-particle amplitude, all right? What's the G counting for this guy? So this is a different kind of amplitude, right? It doesn't contribute, it's a different tensor structure. There's one pattern of deltas that's captured by these single traces. There's a different pattern that's captured by these double traces. But what does this one go like? Well, here there's 1, 2, 3, 4 G's. Okay, so it's a 4-particle clamp, but it still goes like G to the 4th. But there's no more factor of n. Okay, there's no more factor of n because all the colors here are just totally nailed. All the colors on the outside are totally nailed, so there's no factor of n. Right? So that's a Tufts topological expansion. Is all the amplitudes have some overall power of g out in front. So g to some power, which depends on the number of external particles, but the rest is an expansion in the Tufts coupling, g squared n. Okay? And then you can have things that have 1 over n correct. Then you can have these other trace factors. So these are the single traces. You can have double trace, which is 1 plus, and if you work in terms of the Tufts coupling, g squared n, there'll be 1 over n factors associated with it. Okay, so they're subleading in the 1 over n expansion if you cared to do a 1 over n expansion. I want to stress this has nothing per se to do with expanding in 1 over n. This is just an organization of all the tensor structures we can have in different kinds of diagrams. Okay? But it's also true that they have different n counting for this simple reason. So if you go in the usual Tufts limit, you keep g squared n fixed and you make n large, then the diagrams that dominate are single trace planar diagrams. Okay? Already here we see that the double trace is here it just began at 1 loop already. The double traces are just down, and higher traces are down by powers of 1 over n. All right, so we can keep going and talk about single trace at higher loop order. So for instance, I can talk about diagram like this, maybe. Okay. So that's something that we could have at 2 loops. And now what is the expansion here? Now I have 1, 2, 3, 4, 5, 6 cubic interactions. Okay, so this is now going to go like g to the 6th. But now it has 2 powers of n, right? So there's an n here and an n here. So it's a g to the 6th n squared, right? And so again, what have we seen for the 4-point amplitude? We have tree-level diagrams like this. We have 1-loop diagrams like this. We have 2-loop diagrams like this. And this all starts as g squared times 1 plus, this correction looks like g squared n. And this correction looks like g squared n all squared. Okay, so that's, again, the sense in which the expansion is in powers of the Tufts coupling, g squared n. But there's at 2 loops, already for the single trace diagrams, we can have things that are subleading in 1 over n. So what does a subleading diagram look like in order 1 over n? Let me just draw it, and then I'll remind you what the connection is between this picture and surfaces. Let me just draw it the way I'd like to draw it. Put these things anywhere I want, but let me just make my life easier and put them like this. Okay, so here is another contribution to a 4-point amplitude. Now at 2 loops, okay, and this pretzel picture is a donut. It's a torus, okay, and let's look at the color line in this picture. The color line, there's just one color line. Just goes all the way around. This goes like there, poof, 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 around, comes out. Okay, so just a single color line. Okay. There's no factors of n here, right? So this is a two-loop correction. Single trace, but it's a two-loop correction that just goes like g to the sixth with no factors of n squared at all. Okay? So there's a subleading thing here that just goes like g squared n squared times 1 over n squared. Okay? Yes? Yes. Yeah, this graph is not planar. This graph is not the planar. Okay? So I'm just drawing it. I mean, if no, this graph is not planar. So I've drawn it so that these guys are yeah. I mean, this is drawn so that this is going. You see, it has nothing. So this guy's going underneath. This guy's above it. This guy's above it on the other side. Yeah, right. Yes, there's another diagram you could draw that would be planar. Okay, so of course this is a planar diagram. If I just connected them like this is perfectly planar. Okay, and this thing has two factors of n. Right? So I'm taking this and I'm twisting one side relative to the other, right? Yes? That's right, but that's not what I've drawn. I've drawn it so that there's, you see that this, you see it precisely is keeping track of whether there are closed color loops or not. Okay? There's two closed color loops in this picture. There are no closed color loops in that one. Okay, so that's a torus. This is still planar. Okay, so I can draw all of these diagrams. Some of them are planar, some of them are not. I have an expansion in powers of 1 over n if I care to do such an expansion. If I hold the TOEFL coupling g squared n fixed, so there's a standard way that we talk about this, which is that we can organize the perturbation theory, the different color structures that we can have, and the different powers of n that we can have are organized in a topological expansion. And we usually say it in the language of drawing the diagrams on a surface. So we say we draw the diagrams on a plane, or we draw the diagrams on a torus, or whatever, okay? But the point is that at any given order of perturbation theory is associated with some particular, in the standard way of talking about things, some particular topology surface that we're drawing all the graphs on. Normally, sometimes when people talk about this in field theory books, they talk about it in the language of vacuum graphs. Okay? When we're talking about amplitudes, it's not just vacuum graphs, we also have external data, and the external data show up as sort of boundary components. Okay? So, for example, at tree level, there are no vacuum graphs at all, and yet we still have amplitudes. So, at tree level, we would draw a surface where we have n external particles, which are represented as sort of marked points on the surface. And this is a picture we already talked about yesterday. I'll come back to being very specific about how we associate with surfaces and back and forth, but I just want to jump ahead for a second, just to compare to things that you've seen in books. You know, at loop level, people will talk about, you know, vacuum graphs drawn on a sphere. So, okay, so you could draw a sphere, but again, if we're doing amplitudes, you want to, in general, if you have planar diagrams drawn on a sphere, a tree level, or a loop level, you add boundary components. Okay, so you add a boundary component here. So you see, this picture and this picture are exactly the same, right? So I just added a boundary component to a sphere. I just sort of filled in the interior of the disk. But at loop level, I could talk about drawing a torus. But again, if I'm talking about amplitudes, I would want to put in some, I could just have some external data. I could talk about adding some boundary components. Just keep that in mind. We'll come back to describing this in detail in a second. All right, but again, in the usual picture, we're supposed to imagine drawing diagrams on a surface. But there's actually a very closely connected statement, which is the point of view we're going to take today, which is that a single diagram defines a surface. Okay, so these are very closely related, but slightly different points of view. If you want to define a surface, and you're blind, okay, how do you define a surface if you can't, like, see it? Well, you define a surface by giving a triangulation of the surface, okay? The data of a surface is just given by a bunch of triangles, and you have to say how the edges of the triangles are glued to each other, right? This is something always really in all of theoretical physics, but especially in the amplitudes business, it's useful to think about how you would explain something to a computer. Okay, to try to be as algorithmic as possible about what you're actually doing, because you will tend to expose lots of hidden assumptions, biases, et cetera, that you have, that then go away when you're forced to explain it to someone who can't see, who doesn't have the same intuition as you, or anything like that, right? So if you want to define a surface, in fact, there's a wonderful computer program known as Flipper. If you want to play with the surfaces, you'll end up spending some time playing with Flipper. This is the way Flipper is told to surface. You have to give it a collection of triangles and say how the triangles are glued to each other. But let me actually start backwards and say it directly starting from a diagram. So let's say we're given this fat graph, this particular fat graph, this one fat graph, okay? So let's, again, for once, label the color. So this is color 1, this is color 2, this is color 3, this is color 4, right? Okay, now, this diagram defines a surface. How does it define a surface? And I'm telling you this partially, in principle, we don't need this for this lecture. I could in principle, and we will. The entire lecture, rest of today, will be spent on these fact graphs. We're going to live on these fact graphs, okay? And we're going to live on one of these fact graphs. One of these fact graphs is going to define the entire perturbative expansion. So the idea is that at any order in perturbation theory, there is one representative diagram, any one you want to choose. You choose that one diagram, and that diagram defines the surface on which all the rest of the diagrams are going to live. Okay, so that's so I could just stop there and not tell you explicitly how it's connected to a surface, but you might as well know how it's connected to the surface, and the intuition is very useful sometimes to go back and forth between both pictures. But just so you know where we're going to live here. We're going to draw one of these pictures, and that's going to be our world, and we're going to walk around in this world, and we're going to do things in this world, but that's going to be our kinematic space. Remember, yesterday we learned the big deal in this subject is identify your kinematic space and then do something natural there. And now we're going to think about our kinematic space even more dumbly than we did yesterday. By the way, when I say the word dumb, it's always a positive, okay? So clever and ingenious is a negative, dumb is a positive, right? The physics is not about being clever or ingenious or tricks. It might be that at intermediate steps, but it is never about that ultimately. And if someone is saying what you're doing is clever, they're damning you with the faintest of praises, okay? So what you want to do is something deep and simple. We're going to do things that are deep and simple in these lectures, and dumb, the absolute most straightforward possible thing. The thing to do is to figure out how far to take the absolute most straightforward possible thing. That's what takes sometimes some imagination and vision, not from me, but by people like Thurston, who really started thinking about things in the way that I'm going to be telling you about, okay? Okay, but anyway, this single diagram, I want to say the single diagram defines a surface. Now, how does it define a surface? Every vertex defines a triangle. Okay, the vertices of the diagram define a triangle. That makes sense, right? Okay. Now, it's a fact graph, so you can think of the roads of the fact graph. Okay, so let me just call this like road A, this road B, the edges C, right? ABC correspond to the edges of that triangle. So that's one of the funny things, is if someone told you you're defining a triangle, your first instinct is that you're going to define the triangle by giving its vertices. And that turns out not to be the right idea, because for very degenerate small examples, we're going to get funny-looking triangles, okay? But they're all going to have 3 edges, okay? Sometimes they'll have fewer vertices. Some of the vertices will be identified. The triangle will loop in on itself and connect to itself. So if you're labeling it by its vertices, you might run into trouble. It's important to label by edges, okay? So the triangles are labeled by the edges. And then the propagators of the graph tell you how the edges are identified between one triangulation and another, between one triangle and another. Between triangles, how they're glued together. Okay? All right, so in this case, what do I have? I have one triangle here and another triangle here. What are the edges of this? Okay, so if I call this like A, B, C, and then this is D and E, how should I label these triangles? Well, I'm going to label the triangle on the left as AB little c, and I'm going to label the triangle on the right. Oh, and they're all oriented, right? They all have all the surfaces we're going to be talking about are orientable surfaces. So all of these fact graphs are going to define an orientable surface, so they all have an orientation. So the triangle on the left is ABC. The triangle on the right I will write as capital C, DE. So I'm going to have little c and capital C, and that's indicating that the C on one end is going out and is going into the other vertex. Okay? So this is a statement that when I glue these triangles to each other, they're all oriented, and all the internal boundaries have to cancel out. Okay? All right, so what is this surface then? Well, it would look like I have a triangle ABC, oriented this way, and then this triangle, CDE, but when I'm reading C here, it's oriented oppositely to I'm reading it there. So if I'm defining this to be little c this way, then in the other direction, it's going to be capital C. Okay, so that's capital C, D, little e. Okay? So this guy is associated with this surface. Now, we can also identify what are the vertices of the triangulation now, right? What are the vertices of the triangulation? The vertices of the triangulation are the color indices, okay? So for example, here, A is the line that's sandwiched between 1 and 2. Right? So the two color lines that attach to A are sandwiched between 1 and 2. So that's 1, 2. Okay? And all right. So do you see that? So B is between 2 and 3. That's 2 and 3. 3 and 4, 4 and 1, and C is indeed between 1 and 3. So here's the color line 1. Here's the color line 3. Okay? So the vertices of, so finally, sorry, the vertices of the triangle, in the surface are associated with the color indices on the fat graph. All right, so let me try to draw this yet another way. All the same, okay, so, imagine that I'm taking this picture. Let me just sort of add a boundary at infinity. Just, all right? And you see this region 1, that line is 1, so I can kind of imagine that the whole region underneath it is associated with the color 1, right? And this region here is associated with 2. This region here is 3. This region here is 4. Okay? So that's what I literally get from the fat graph, right? Now, just take this picture and shrink the regions 1, 2, 3, and 4. Okay? They're not part of the surface, right? They're kind of outside. Now just shrink them. What happens is you shrink 1 and 2 and 3 and 4. If you shrink black regions, then this goes over into okay, is that clear? And yesterday we talked in the language of drawing the dual diagram. Okay, so if you now, that's another way of getting the surface, and I'll leave it as an exercise for you to see why these ways are all equivalent to each other. All right, but if I say this now more generally, any surface is defined as any surface, any orientable surface, is just defined combinatorially, is defined by the data, by the combinatorial data of a collection of AI, BI, CI, or a collection of triangles ABC, where everything can either occur as lowercase or capital case letters, okay? And every index, every edge, can occur at most twice. And if twice, it has to occur both in lowercase and uppercase. All right? That's the statement that they're, again, in the propagator language, it's just a propagator going across. In the triangulation language, I can have two triangles. They can only meet, they're either boundaries, or if they're not in the interior and they have to meet, they can only occur twice, one on one side, one on the other, and their orientations have to cancel, okay? That's the data, right? That's it. So any collection of triples ABC that satisfies these properties defines a surface. Once you so define it in terms of edges, you can work out what the vertices are, right? So how are you supposed to work out the vertices? Well, for every triangle, you write A, for every triangle individually, you write A is equal to V1, V2. B equals V2, V3. C equals V3, V1 for some ersatz vertices. You don't know what they are ahead of time, V1, V2, and V3. And then you just write that equation down for every single triangle. But for some of the edges, they're going to occur twice. So that's going to give you relations between what you mean by the V's for the capital X's and for the V's for the little x's. And that's just a ton of linear equations you solve and you determine all the vertices are determined by this data. We could spend like 45 minutes having a lot of fun, drawing lots of pictures and showing how all this works, but I don't actually want to deprive you of that fun. So an exercise that you can do maybe if you want to do it over lunch or something, we could talk about it afterwards, is just draw all the surfaces that are made out of two triangles. Okay, I give you one of them, and there's a few more. Okay, they're not too many. You'll find the annulus, you'll find a torus, you'll find a sphere. So you'll find a lot of nice surfaces, and just draw them in this language, and draw the corresponding fact graph, and just see what they all look like. Okay? All right, so our fact graphs are associated with surfaces. The normally way we talk about them is we draw the fact graphs on surfaces, but we're now going to take the point of view that a fact graph defines a surface as well. And so any given order of perturbation theory is just assigned to a single diagram. It's not a Feynman diagram, it's a color diagram, right? You're trying to describe the tensor structure of the order in perturbation theory that you're in, and I'm just describing that tensor structure by telling you how to glue a bunch of deltas together that correspond to the 3-point vertices, just to tell you which order that we're talking about, okay? One diagram. All right, so let's now come back to tree level and say we have our one diagram. Let me draw it at 5 points just for fun. Okay, so here's a one diagram that's describing a particular triangulation of now the disk with 5 points on the outside. Okay, so what is the triangulation that this corresponds to? What's a fast way of seeing what the triangulation is? We'll just see what the internal roads are, right? So for now, I'm going to just label the roads. This is unambiguous here. Later, at higher loops, sometimes it's ambiguous, and then I'll just label the roads directly. I could label the roads A, B, C, D, E, F, G, right? But let me just label them by the sort of regions that surround them. So this road here I'm going to call 1, 2. That road I'm going to call 2, 3, 3, 4, 4, 5, 5, 1. So this road is going to be called 1, 3, and that road is going to be called 1, 4. Okay? Is the notation clear? Okay. And so, okay, well, the guys on the outside I have drawn in this picture already, so I also have this road 1, 3, and this road 1, 4. Right? So that indeed gives me a triangulation of the disk with 5 points on the outside, right? Triangle, triangle, triangle. Okay, that's the corresponding triangulation. All right. Now we're gonna we want to keep on going. So this defines our playground now. But remember, yesterday we talked about the kinematic variables, and we immediately talked about the variables associated with general propagators, right? Those xij. Now we did it without thinking, and we just called the xij, and it was great, and we went off and we had some fun. So today we're going to take even a step back and think about how to better label those xij's. But before we do that, let's just sort of talk about things in this language, though. Going back to the picture of the surface for a second, let's forget about the fact graph for a moment. Going back to the surface, what are the all the Feynman diagrams are triangulations of this surface, okay? We talked about yesterday what are all the variables that we see correspond to chords on the surface. Okay, so here's a chord, here's another chord, okay? These are crossed so they don't occur together in diagrams, but in any case, all the variables are associated with chords on the surface. Let's do a slightly more complicated example, just because we're just doing sort of kinematical things for now. Let's go back to this fact graph. Okay, what surface do you think this corresponds to? This looks like a disk with 4 points on the outside. Okay, but what does this color loop on the inside correspond to? Remember how we got it, right? We got this picture, and then we took all the black regions, so this is going to be a black region too. We took all these black regions, and we contracted them to a point, right? So this interior region here, the color line that doesn't end anywhere, the pure interior color line, collapses to just a little marked point on the inside, okay? Just notationally, these things that are marked points on the inside are sometimes called punctures, right? So this is a puncture. I don't know why they like these fancy names, but anyway, it's a hole. I call it a hole, but you can call it a puncture, okay? But we'll put a little X there. Okay, and now what is this triangulation? This fact graph corresponds to which triangulation? It's the pizza triangulation, the pizza slice triangulation. Okay? So this is another example. And so in this picture, once again, what are the kinematic variables? Okay? My kinematic variables are, well, for example, I still have, let's draw this again. I can have variables like I did before. For example, at 4 points at tree level, I had a variable like 1, 3, right? Now that I have a puncture, it's slightly more interesting because I can have 1, 3 that goes around this way or the 1, 3 that goes around that way. Okay? This has to do with the fact that if I draw, so here is a fact graph that would contain them. 1, 2, 3, 4. You see, there's this 1, 3 would correspond to that propagator on the left of the bubble, and this 1, 3, 3, 1 corresponds to that propagator on the right of the bubble. Okay? So these are really distinct curves when it comes to the picture of the triangulation. So already here we see an interesting little thing that we think, when we think in terms of curves on the surface, there are more curves on the surface than there are strictly, literally propagators that we see in the Feynman diagrams. The curves are generating the diagrams for me, but they have a little bit more data of like where the variable is going to occur, for example. Okay? So those are going to be assigned the same momentum, but there are different curves on the surface, and it's healthy to think about them as different propagators too. Okay? Later we'll identify them, but they're actually different propagators in the graph. They just happen to be assigned the same momentum. Okay? This phenomenon ends up happening on steroids in this business, and in fact, there are infinitely many curves end up being assigned the same momentum, and there's a whole interesting story about infinity that we probably won't talk about today. I'll talk about probably tree level in one loop, mostly where this planar one loop where this phenomenon doesn't happen. Okay, but already we see, so we have this curve and that curve, they're assigned the same momenta, but they're different curves. What about some other curves? Okay, so here is another curve. Okay, and who is that curve? Which propagator is that curve? It's like this kind of propagator. Right? It's the loop propagators. The loop propagators are the things that go to the punctures. Okay? Okay. So propagators are chords on the surface. All right. What are Feynman diagrams? So Feynman diagrams also have a nice interpretation. I'm just translating things back and forth. Feynman diagrams are associated with a maximal collection of non-intersecting chords. So this generalizes what we saw yesterday at tree level, where the Feynman diagrams were triangulations of the disk. In general, a Feynman diagram is the same as giving a maximal set of non-overlapping chords. So let's look in these one-loop examples. Well, here's one, right? And that's associated with this fact graph. Here's another one. Okay? You see that this is a triangulation? Triangle, triangle involving a puncture, triangle involving a puncture, triangle. Okay? And this triangle 1, 2, 3 is that one. Okay? This triangle here is that one, and that one. Okay? Of course, you see equally well, if you take either one of these two pictures and you shrink the black regions, you get the same picture. You get the same picture of 4 points on the outside and a puncture on the inside. But the fact graphs tell you more. They also tell you a particular triangulation. Okay? So a maximal set of non-intersecting chords is what you could call a triangulation of the surface. It gives you a triangulation of the surface and is associated with a Feynman diagram. All right. All of this is true for any surface. Okay? We can draw arbitrary, for arbitrary surface, arbitrary order in the topological expansion. All right, let me just keep going with the dictionary, because what I'm doing now is just setting up what our kinematic space is, right? At any loop order, we're just setting up how to think about our kinematic space. So the final thing to talk about is how do I assign momenta to propagators? Okay? Now let's think about how we did this at tree level yesterday. And at tree level yesterday, at some early point, I just drew this n-gon, and I just said, oh, let's look at the distance squared between points, and it was all very nice. The classic example of a trick, okay? And you know a trick is a trick when it doesn't work. You see, either a trick keeps working, in which case there's something conceptual behind it, or it doesn't work, in which case it's not quite the right thing. And so people have tried to define, this is a kind of long-standing problem in the amplitudes business. How do you define what you mean by loop momenta for non-planar diagrams? Because there is, you know, in general, if you have random Feynman diagrams, it's not obvious how to combine them all together into a single integrand. Because it's not obvious what you mean by the loop variable in one diagram compared to another diagram. What do you mean by L? You put an L in some random spot here, another L in some other random spot in another diagram. How do you know how to line up the L's between each other, right? Well, when we have planar diagrams, we can do it. We can have planar diagrams. There's a sort of well-defined notion of what L means. And using these dual variables that we talked about yesterday is one of the standard ways of making that manifest. But it doesn't work for non-planar diagrams, so you're stuck, right? What I'm telling you about now is what solves this problem. There is a canonical way of talking about loop momenta, any diagrams, planar or non-planar. But it begins with a slightly different way of thinking about it already in the planar case, already at the tree level. Okay? So now we're not doing, now this picture is not a trick anymore, because we really are associating this surface even back at tree level. Okay? But somehow, definitely, we're not going to do better than saying that, you know, propagator is associated with a curve like that, right? That was clearly a good idea from before. But that's a slightly different point of view. Now we imagine that there are really momenta associated with this picture, P1, P2, P3, right, to Pn. The momenta are associated to the boundary components of this space. Now the idea is that you draw any curve you want, and any curve you want is going to be assigned a momentum by its homology. Okay? So what that means is if I draw this curve, I don't have to draw it as a straight line. I don't have to say that it's xi minus xj squared. In fact, I'm not talking about those x's at all anymore. I'm not saying that p is xi minus xi plus 1, nothing like that, right? The x's are gone. I'm just drawing momenta. But I have to tell you what the external momenta are, one way or the other, so that here they are. But this curve or that curve, I could draw it any way I want, it doesn't matter. All of these curves are homologous. That means that you can, continuously deform them to be the same as this boundary curve. And so the momentum that you assign them is the momentum you would assign to that boundary component. Okay? Isn't that cool? So if you have an I and j, this would tell you that xij is indeed pi plus dot dot plus pj minus 1. Now, that's the momentum that you would assign to it, but there's a little ambiguity of whether you decided to do plus or minus, right? So that's why you square it. So it doesn't matter, right? So if you square, which is what we see in the propagators anyway. Okay? What is momentum conservation in this language? The fact that a closed loop is homologous to 0, right? Right? So momentum conservation is also a homology statement. But now let's keep going. Now we can use this idea at any loop order we want. So let's do one loop. Okay, now one loop, there's just a little issue. So if I call this P1, P2, P3, P4, P5, I guess, right? Now, if I give you all of these momenta, I'm not entirely done specifying a basis for the homology, okay? Because there's also this curve. I can't determine the momentum of that curve from any of the other momenta, so I have to choose one. Doesn't matter, it's a basis choice, choose one. I'm going to give this guy a name, L, okay? Now I'm done again. Draw any curve you want, and that curve is assigned a momentum by homology. Okay, so what is the momentum of this curve? What's the, well, or the momentum squared. This is P3 plus P4 squared. But what is the momentum of this curve, for example? Okay, well, that guy, I can deform it to this plus that. So that is assigned L plus P2 squared, right? And that's, of course, exactly what you assign from drawing the corresponding Feynman diagrams, right? But the cool thing here is that you choose one basis once and for all, and every other curve, any other curve, you might not see that curve in your triangle, any curve on the surface is unambiguously associated a momentum. Planar, non-planar, doesn't matter, okay? Everything is unambiguously assigned a momentum by this rule. So momenta are homology. Okay, so this is, now we are essentially set with defining our kinematic space, okay? There's a lot of novelties that emerge when you start looking at things starting with the annulus and beyond, because some infinities show up. I've alluded to this infinity once already. Well, maybe I'll just tell you quickly. When you draw the annulus, so something like this, let's say. Let's say 1, 2, let's say 3 here. This could correspond to a fact graph that looks like this. Okay? So this would be 1, 2, and this would be 3 on the inside here. Okay? Okay, so these are not planar diagrams. And now there's a little novelty, which is that, I have this momentum. That would be some loop momentum, let's say, right? I have this graph, I have this curve, but I also have this curve. And I have this curve. And I have infinitely many curves on that surface, okay? Why do I have infinitely many curves? Oh, and so what is a Feynman diagram? Again, a Feynman diagram is a triangulation. So let's say we draw this. Let's just draw one. So here's a triangulation. Okay, that's a little triangulation. And this is one of the examples that if you did it, you'll see over lunch. The triangles look a little bit funny, right? So this is a triangle. Here's a triangle. You see, it's a triangle indeed, but it's a little bit degenerate as the vertices look. But it still has three edges. They all have three edges. The key point is they all have three edges, okay? So this is a triangle, triangle, triangle. This corresponds to this fact graph, not that one. These are all just practice for you to see what the fact graphs look like. It looks like that fact graph, for example, okay? But now, take this picture. Imagine, yes? Yes? That's a good exercise for you over lunch, okay? To see how this picture turns into that one. It does, okay. So, but again, the business about shrinking is for intuition. The thing which is completely concrete is that both pictures are a list of triangles with rules for identification. Okay, the graphs are a list of vertices with a rule for identification. The surface is a list of triangles with rules for identification. That's it. Okay, and then the formula for and since it's the edges of the fundamental things that are given, you derive the vertices, and the vertices are the color lines. Okay, so that's why there's a one-to-one correspondence between the data on both sides. But on this side, there's something that we're not seeing here. On this side, if I take this picture, and now I imagine, so these are three non-intersecting curves, a maximal set of non-intersecting curves. You draw anything else, it's going to intersect one of those guys. But if I take that picture, I take the inside, let's say, and I just spin it 360 degrees, I'm not changing the fact that they're not intersecting. But I'm going to get a more swirly picture. Okay, I make it go twice, three times, any number. I get arbitrarily swirly pictures. Okay? So that's a novelty. Now there's sort of, what we're getting from the surface is actually, because of this distinction that we're making between propagators, we're getting infinitely many copies of the diagrams. Okay? There's actually good reason for that. How do those things differ? These different diagrams, if I take this picture, and I take this guy and I rotate everything once, right? It's the same fact graph, but what do the momenta look like? See, after I rotate everything around once, every curve is going around the inside one more time. So in its homology, you're adding Q to it, where Q is the total momentum, let's say, on the inside ring. Okay? So the second diagram that I'm getting is exactly the same as the first diagram, but I'm shifting the loop momenta by Q, right? And remember, here we're still sort of talking about things that could look like an integrand, and there's this whole question of how we line up loop momenta between different diagrams and so on. And this is the price for being able to talk about all loop momenta in a totally canonical way, is that now you have different diagrams that'll just differ by translations in loop momentum space, and what you naturally get from the surface is all of them put together, okay? So that means eventually, we're not going to talk about it so much today, but eventually you have to figure out how to keep one copy of all these diagrams. At the level of the surfaces, we want to mod out by this obvious symmetry, where it says you take the interior annulus and you just spin it some number of times. Okay? Now, in the ancient, now over 100-year-old mathematical understanding of surfaces, the space that we're talking about is called the Teichmuller space. You don't need to know anything about Teichmuller space. You don't need to even have heard the words. Turns out Teichmuller was a terrible human being, by the way. I only found this out recently. He was a Nazi, terrible, okay? Really, really awful guy. So anyway, let's say his name less, if we possibly can, right? So, but this space is called the Teichmuller space. But what we care about, it has this sort of obvious infinite symmetry that's known as a mapping class group. And the mapping class group is what you get precisely by these things where you take the little, in this case, the little annulus, and you just spin it any number of times. In general, it's a giant non-abelian group. There's something that we care about when we want to keep only one copy of all the diagrams. We want to mod out by this mapping class group. We want to identify things up to the action of the mapping class group. And the space that you get when you start off with Teichmuller space and mod out by the mapping class group is called the moduli space. Okay, so these are the two things. There's the Teichmuller space of Riemann surfaces, the moduli space of Riemann surfaces. So we're going to need to learn out how to mod out by the mapping class group. Okay, but this is all. If you've heard of these things before, you can totally ignore it for the rest of these lectures. I might say a little bit about it depending on how we're doing for time. But at tree level and through to one loop, we don't see this. Yet. Okay. All right. So now we're almost done, and then we'll take a little break and resume. We're almost done defining our kinematic space, except what I want to do now is say absolutely. So here we went back and forth. We talked about fact graphs, surfaces, dictionary. This is mostly to sort of build some intuition. But now I just want to be like super concrete and say everything in one picture, one language, which is the language of the fact graph. Okay? We're going to define our surfaces that we're talking about by a single fact graph. Okay? And so on that single fact graph, I want to do everything. In principle, I never have to stare at the surface ever again. I'm just going to play with the fact graph. Okay. But here there's a little interesting move, which is the move from what I've been calling so far chords, and none of you complained, because it was clear what I meant, to something that I'll call arcs. Again, the fancy surface people call these laminations, but I'm going to call them arcs. Okay? And let me explain what I mean already again back at on the disk at tree level. So for example, we've been drawing sort of curves like this, like 1, 4, without thinking about it, all right? But if you think about it, this is a little bit funny. This is going from 1 to 4, but 1 and 4 are exactly those black regions. They're not actually on my surface, right? 1 and 4 are not actually on the surface. There are the holes that are not there in the surface. A little funny to label curves on the surface where the start and end points of the curve are not on the surface. Okay? So these are chords, perfectly fine. The chords are defined as things that if they have endpoints, they end on marked points or punctures. Okay? But we're instead going to talk about, so these are chords. We're instead going to talk about laminations, or arcs. And that's the following idea. For the same guy, I'm going to take exactly the same curve, and I'm going to make it defined on the surface by just pushing the endpoints a little bit. Okay? So I'm going to push the endpoints so that it looks like this. Let me use a different color. I guess I don't need to use it. Oh, okay. Okay, so this is the arc associated with the chord 1, 4. Or this is the chord associated with the arc 1, 4. Okay, you can go back and forth between them. Why is this well defined? It's because we have an orientable surface. So when I say push the endpoints, I mean push the endpoints in, let's say, always clockwise, according to the orientation of the surface. Okay? So here, there's a little orientation that's going around this way everywhere. So I start here, and I push the endpoint that way. And here I push the endpoint that way. If I had an annulus, let me draw an annulus again. Say I have this chord. What is the lamination for this guy? Exactly the same picture. I push it in this orientation, okay? So that means that I would get something like this, okay? And so on, okay? So this is meaningful for any surface. Here I drew it in the language of the surface, where maybe it seems a little bit funny to talk about pushing the endpoints. But on the fact graph, it's completely beautiful, okay? So let's talk about what we're doing on the fact graph. Of course, on the fact graph, it's the chords that look a little funny and the arcs that look reasonable. So if I draw, let's say, at 4 points, again, if I draw a fact graph, and this is the corresponding triangulation. Okay? What do the chords look like in this picture? So like, what does 1, 3 or 1, 2? So this triangle, maybe I should have said this before. Let's look at this triangle, this sort of standard triangle that I'm drawing on the surface. What does that look like? Well, what does it look like on the fact graph? Well, this thing 1, 2 is something that's connecting 1 and 2. So that would be, I should have done this before as part of our dictionary. Sorry, it might have also helped. So 1, 2 would be something that looks like that, right? It's connecting region 1 and 2. 2, 3 looks like that. 3, 1 looks like that. So this triangle here is like this little triangle here. That's exactly what we said before, is that the vertices are triangles. Okay? But now, what is this lamination? What is this arc? So if instead of 1, 3, I'm talking about this arc, what is that arc? That arc is something much more reasonable. It's just a path on the fact graph. Right? It starts somewhere here on 1, 2, so it's starting here, and it goes to 1, 3, and it goes out on 3, 4. Okay? So an arc corresponds to just a road that you walk on along the fact graph. Right? What could be more natural? Right? So what are our variables now? Now we can say everything in the language of a single fact graph. We have our kinematic space. And now let's finish our dictionary. So what is our kinematic space? What's our playground? We have a single fact graph to define the surface, to define the color order that we're working with. Okay, that just defines the order. The propagators are going to be associated with arcs on the fact graph. Feynman diagrams are associated with maximal collection of non-intersecting chords, but if I push the endpoints, they're non-intersecting arcs. Okay, it's exactly the same. Now, a very interesting question, which we're going to talk about, is how do you know whether arcs intersect or not? Okay, that's another thing where I draw it on the fact graph and I see with my eyes that they intersect, but we're going to, no seeing, we're going to have to learn what intersection means. There are all kinds of things we're going to have to learn very canonically. All right, but finally, let me tell you what momenta are in this language, and then we'll pause. What are momenta? Well, remember, momenta were homology on the surface, but now I wanted to find what momenta are in the language of the fact graph. Okay, so remember, a propagator is associated with an arc. So what is the rule for momentum? Let's draw this example. So what you do is you assign your parent fact graph also some set of momenta, okay? Tree level, loop level, whatever. So that just is going to give me the basis for homology in the other language. Okay, so in this case, I do it by saying P1, P2, P3, P4, P5. Okay. But now I want to know for any old graph, so for any old arc, so let's say this arc, okay? What is the momentum that I'm going to assign to that arc? Okay. And the rule, the homology rule, translates to the following. It's really simple, but I won't prove it. You can prove it with a tiny bit of thought, but let me just tell you what the rule is. The momentum from any curve it starts somewhere. The curve starts somewhere. So it's P start plus, and you just follow the curve along, and everywhere you make a right turn, you sum over all the momenta that enter from the left. Now, why is it reasonable there's a left-right dichotomy here? Well, because remember, even at tree level, we have to decide in defining the momenta whether it's going to be around one side or around the other side, right? If we did it around one side, we'd have plus sign. If we did it around the other side, we have minus signs. So you've got to choose whether the momenta, you're counting the momenta coming from the left or from the right, okay? And this is the rule that for any surface is equivalent to the statement about homology. So let's see how it works in this case. So here we'd start with P2, right? Here I'm going to make a left turn. In the next lecture, we're going to have a lot of fun with these left and right turns, okay? So the whole story is going to be about these left and right turns, but we already see it here for momenta. Left turn, nothing here. Here we make a right turn, so I have to add the momenta that was entering from the left, which is P3, right? And I make another right turn, and I have to add the momenta that's coming from the left, which is P4. Okay? So here, the total momentum P mu would be P2 plus P3 plus P4. And of course, this is exactly what we associate with the same curve, with the chord that we were drawing beforehand. Okay? So so that's the momenta that we associate with this curve. Yes? No, I mean, so at this juncture, I'm making a right turn. If I make a left turn, I'd go left into P3. So at this turn, I'm making a right turn. Okay. So at the juncture, so the turns are made at the vertices. You really think that? Well, we'll talk about this a lot in the next lecture. But we really think you're like driving along the road, and then you hit a three-way juncture. Okay, and you turn left or right. If you turn right, then there's a unique road coming at you from the left, and you add the momentum coming at you from the left. Okay? All right, let me do one more example, and then we'll break. There's a slightly funny thing about arcs when we have punctures. So I'll just draw this picture, and then we'll stop and talk about the rule for momentum. But let's say, just going back to the surface for a second, because I defined things. So let's say I have one of these curves. See, one of these curves corresponds to one of these curves corresponds to the loop, the propagators that carry loop momenta, right? So how would I make an arc out of this? I want to push the endpoints of this guy, right? All right, that's fine. So I can push the endpoint on this side and push it over there. What am I going to do over here? Not obvious what to do, right? Okay, well, this will not look obvious immediately, but it'll make more sense as we go on. What you're supposed to think about it as doing is actually spiraling around forever, okay? So it tries to end. There's this hole. You should think of this puncture as a little hole. That hole has no marked points on it, right? So all you can do is keep on going forever, okay? You can spiral around one way, or you can spiral around the other way. You can spiral around in either direction. So there's sort of two kinds of spiraling variables. Okay, I drew that going. Anyway, we can go around one way or we can go around the other way. Okay, so we have two kinds of spiraling variables. Looks a little bit funny, but you'll get used to it. It turns out that there's a complete symmetry between these two sets of variables, so we don't have to keep both sets, okay? And for some purposes, it's going to be useful to have both sets, and for others, we won't need them. In particular, for thinking about assigning momenta and the actual Feynman diagrams and the amplitudes and so on, we're only going to keep one copy. And in that case, by convention, we'll keep the ones that spiral counterclockwise. Now let's think about what this looks like on the fact graph. And again, why there's no choice but to spiral. So let's draw this diagram again. And what does one of these spiraling curves look like? Well, you know, I'm coming in. All right, and I go around, there's just no place to go. So I'm just going to keep going forever. Right? These curves that I'm drawing, I should have emphasized, are non-self-intersecting. Okay? I could also draw curves that self-intersect. And if we get to it late this afternoon, you'll see there's a set of ideas here that turn these pictures into string amplitudes. But there's various kinds of string amplitude that you could be talking about, things that we call baby strings and full strings, and the distinction between them depend on whether you do or don't include self-intersecting curves in your story, okay? But here, all the things that we're talking about, propagators, Feynman diagrams, implicitly they're non-self-intersecting curves, right? So you see the problem. Once you start spiraling, you're stuck. You have to keep going forever if you're not going to intersect, okay? So that's it. Okay, you spiral around forever. But the cool thing is, by this rule, you still get assigned an unambiguous momentum. And the reason is that the way I've done it is that, oh, sorry, I did it exactly wrong, because this is something that's spinning clockwise. If I draw the ones that spin counterclockwise, by this rule, the infinite part, it's always turning left. So I'm not adding any momenta here, all right? And in fact, I do assign some momentum from the right turns that I made, and those momenta are exactly what you'd call the usual loop momentum variables, the same momenta that we assign to the chords when we're talking in the language of chords, okay? All right, so momenta are associated with this P for any curve x equals P start plus sum over right turns P left. And now we're really done. Okay? This is our playground for the rest of today. Right? We draw one fact graph to define the color ordering. These are our variables. We know what we're supposed to get. We're supposed to get one copy of all the Feynman diagrams. Somehow, Feynman diagrams have to We have to think about why we care about diagrams. We have to add them up. All the stuff we talked about yesterday, but now in this setting, where we've now defined what we mean by the variables at any order in the perturbative expansion of this theory. Okay? So we'll start with this when we get back after coffee. Yes? Yes? Yes, yes, it does. Yes. So for example, let's see what the rule is, right? So let's say that in this case, I assigned this guy to have momentum L. So let's say this is P1, P2, P3, P4. Okay? Then the momentum that you would assign to any curve in this picture is the same as it was before. You enter the picture, you just add. So for example, here I'd start with P1, and I'm making a right turn here, right? So I'm making a right turn, so I'd have to add the momentum that's coming from my left. Okay, so who's coming from my left here? If this is L, then I have to track it around. So this is going to be L minus P1, right? So I just keep on going, L minus P1, L plus P2, right? The usual thing, L plus P2 plus P3, say, right? Going around like this, okay? Yeah. Sorry? Well, that's right, which is good. You see, so let's see what momentum we assign to this graph. So here we make a right turn, okay? So I start with P1, but I add L minus P1. So now I have L, right? Now I make a left turn, I add nothing. I make a left turn, I add nothing. I make a left turn, I add nothing. So now I add nothing forever, okay? So what I get is L in the end. See, the momentum that I get is, by this rule, P would be P1 from this guy. I have L minus P1, and then I have plus 0 forever. Okay, so I get L. Now, if I did it for this guy, now what would I get? Now I start with P2. P2, in here I'm making a right turn, so I have P2, and then I have to add the momentum that's coming, right? So I define this to be L minus P1 out, so it'd be P1 minus L in, so it's P1 minus L, right? And here I'm making a left turn, so I add nothing, and it's nothing forever after that. Okay, so I'd assign P2 plus P1 minus L. Good. Okay, that thing squared is the propagator that I would associate with this picture. I mean, the actual propagators that I'm supposed to get is something like L plus P4, L plus P4 plus P3, L minus P1, and so on, right? L plus P4 plus P3, which is the same as L minus P1 minus P2 here, right? So these are all the momenta that I would be associating with this picture. This is why it matters that we're only talking about spirals going around by convention counterclockwise. If I was talking about the clockwise one, the momenta would be infinity, right? Because as I keep going around, it just keep adding. You could imagine doing that. If you did that, the thing is you'd assign all of these guys infinite momenta, so they would not occur in the Feynman diagrams. When you wrote 1 over momentum squared, it would be 1 over infinity, so they don't show up in the diagrams. That's another way you could say it. We're not manually throwing them out, but the other ones just don't show up. Okay?
Okay, so in case you have any further questions, I suggest you ask them privately. Let's thank Nima again.